Hello, and welcome to Visible Spectroscopy by Robbie Freeman. So, what is visible spectroscopy? Well, visible spectroscopy is a measure of what wavelengths of visible light are absorbed by a sample. It provides qualitative and quantitative data on these things, the qualitative data being what precise wavelengths are absorbed, and the quantitative data being the absorption, or physically how much of the wavelength is absorbed. Why is spectroscopy useful? Well, it's more accurate than human eyes, it's less subjective than human eyes, and it's simple and effective. Useful in many applications such as testing concentrations or finding the exact colour, as you'll see in the next slide. So, what was done in the lab? The lab was divided into two parts, and before both parts the spectroscope was calibrated using water in a cuvette and waiting for the spectroscope to heat up before calibrating on the computer. Throughout, we made sure to only handle the cuvettes by the frosted side, and that when testing the cuvette it was seated properly by pushing down with the clear side to the side with the arrow. In the first part, we took samples of 7 different inks and placed them into a cuvette, filling it to about 3/4 full, before it's placed in the spectroscope and a test was run on the computer, where the computer logged the data as a graph, and the highest peak and wavelength was recorded into our lab books. It was then repeated with all 7 inks. The second part was a little more involved, where we used 5 volumetric flasks and prepared 5 concentrations of lime cordial. These were 20, 40, 50, 60 and 80% solutions. They were then tested in the spectroscope and the resulting highest peak was recorded. Final unknown concentration of cordial was tested 3 times and each result was recorded. The final cordial was tested 3 times so that an average could be taken and compared to the rest to find the unknown concentration. So, as you can see, these are the results from the ink part of the practical, and as you can see, black is the only result gathered to have an absorption above 1 and also that has all wavelengths absorbed. However, as you can see, all the other colours also have quite varied different amounts of absorption and quite varied different amounts of wavelengths. What does that mean? Well, here are the results next to the visible spectrum of light. And this is the colour wheel. So, each ink absorbs a different wavelength to a different degree. This is because each ink has its own colour, and colour is dependent on which wavelengths are absorbed. So, as you might have spotted, if you look at the wavelength and then take the wavelength and move it into the spectrum, you can see that it actually reflects the opposite colour on the colour wheel. So purple, for example, is 527.6 nanometers, which is roughly around green, and if you look, the green is opposite purple. This is because colours absorb the colour opposite on the colour wheel, because the wavelengths you're seeing and the colour you're seeing is dependent on what light is being reflected off the object rather than absorbed. So when the opposite colour is absorbed, more of the colour you're looking at is reflected and therefore you see it. As you can see, here are the results to part 2 of the practical. This is the part with the lime cordial. As you can see, all the wavelengths are nearly the same. They're roughly all about 390 nanometers. This is because all the cordials are the same colour. However, you can see as the concentration increases, the absorption also increases. This is because of the slight green colour of the cordial, which increases as the concentration increases. So it gets more saturated, so there's more absorption of the opposite colour wavelengths. The point of the second part of the practical was to work out the unknown concentration of cordial. So, time for the maths. As you can see, I have plotted the given concentrations and their absorptions on a curve. So we'll need the average of the 3 tests we did of the unknown cordial. To do this, you take the absorption of each 3, add them together, and divide that total by 3 to get the average, which is 0.084. This was quite easy because they all gave the same absorption. The average is 0.084, which is roughly about here on the curve, which gives us a concentration of around 30%. Those are the two parts of the lab we conducted, and in conclusion, these are just two ways spectroscopy is used to analyse a sample. It's quick, simple to do, and cheap to run, but it does have limitations, as it tells us very little about the actual chemical in the sample, other than its colour. However, when used with other tests, it can provide a useful piece of evidence for what chemical the sample contains. Thank you for watching, and I hope it was informational in some way.